Buenos días a todos nuevamente. Antes de comenzar la siguiente presentación, les volvemos a recordar que durante toda la sesión van a estar sus micrófonos y cámaras apagados. Y nuevamente que las preguntas que surjan durante la presentación las deben hacer por escrito en el panel preguntas y respuestas que van a encontrar en el margen inferior del menú Webex con las letras P y R. Las mismas las leeremos sobre el final de la presentación. A continuación, entonces, le vamos a dar la palabra a los disertantes del trabajo titulado Evaluating Performance Potential of Undrilled Vaca Muerta Blocks with Machine Learning. Bajada del Palo, Oeste, Case Study. Sus autores son Ted Cross y Kiran Sathaye de Novi Labs. Ted, welcome, and please go ahead with the presentation.
Thank you, Adrian, and thanks to IAPG for organizing this conference and for the invitation to speak. You are all in luck today. We have back-to-back talks from Austin, Texas, about with some blind holdout test sets from the Bajada de Palo Oeste. You'll see that we've taken a slightly different approach from the previous presentation. So it's good when this type of stuff happens at a conference, so you can see kind of how different methods can result in different results. So the motivation for this talk, as the Vaca Muerta has matured, methods for evaluating the prospectivity of blocks and undrilled locations must keep pace with the increasing volumes of available well data. There are now over 500 producing wells available publicly in the basin, so machine learning and other advanced statistical methods are trained on wells in basin can complement and accelerate traditional valuation methods. So to test this approach, what we took today is an artificial pre-drill or pre-lease scenario where we took all the wells on the Bajada de Palo Oeste block and put them into a blind holdout test set group and ran our evaluation on the block. For input data, we're in the Vaca Muerta. It's exclusively the Vaca Muerta, no Jurassic formations were used in the training data here. For input variables, we have, for completions, we have proppant and fluid volumes as well as stage counts. For spacing, we took the number of co-developed siblings at a pad location. For timing, we took the number of parents and time. For geology, two-way travel time and transformation ratio maps. We cut off the production at March 2020 to avoid any shut-in data issues. One thing to note here is that the bottom hole location is not available publicly, at least nowhere that we or any of our collaborators have been able to find. If you know where it is, let me know. So we kind of make up a bottom hole location. So this means that you can't use kind of standard metrics that you would use in like a North American basin where the survey is available for, distance in zone or, number of wells per section, those type of metrics. We also want to note that we did not include operator. So that's a powerful categorical variable, and it can kind of obscure the drivers of the actual production, so that's excluded. We don't have any latitude, longitude, area, or block variables included in our model, and we don't have any post-drill operational data. For filtering criteria, we limited it to wells that had at least 90 days of production. So that means, if it would have just come online, we're not using it yet. We threw out outlier completions values, mostly for this basin that was stuff down at the very low end, pump and pray style completions, etc. We limited it to only wells with lateral length greater than 300 meters. For this model, we used wells just from the oil window, and this left us with, after all that filtering criteria, 315 wells for training. And all the data here was just downloaded from the Secretaría de Energía's website. So very clean, well-organized public data set, so compliments to the government for that. Just a little bit on the input geology data here. when you're evaluating block prospectivity, it's really the regional geologic trends are responsible for the majority of kind of what drives the production in that individual block. And for this, we just used very simple geologic model, digitized a couple kind of published grids. We had seismic two-way travel time and transformation ratio. So these are kind of proxies for depth in the case of the seismic and for maturity in the case of the transformation ratio. I've noted the location of the Bajada de Palo Oeste block there in purple. You'll see that the kind of strike for both the seismic travel time and the transformation ratio is northwest to southeast, with both the maturity lessening and the depth shallowing to the northeast of the basin. So for model training, the algorithm we used, it's decision tree based, and it's extremely random trees. It's similar to a random forests model where it creates an ensemble of different decision trees that creates a robust model, and it's does well at avoiding overfitting compared to some other algorithms. These type of algorithms can handle numerical and categorical variables. And the basic way that it works, if you look over at the cartoon over there on the right of the slide, is that you start with all of the wells in a pile where you have a certain average production value. And then the tree will split them according to one or more of the input variables like water saturation, proppant values, or spacing. And at the end, what the tree is attempting to do is to split the wells into groups of production, so high producers, low producers, medium producers, etc. And this gets repeated many thousands of times across many different trees. They can grow a lot larger than this. They can split on multiple variables at once. But that's the basic idea, is that it's almost similar to an analog type curve process where the reservoir engineer chooses a set of wells that they think are analogous, and that becomes the basis for their type curve. So in some ways, it's similar to that. So we split out a random 20% of the wells for model evaluation. That's our standard. But then we also took the Bajada de Palo Oeste wells and we put those aside as well. So we have 20% of the wells in the basin plus the Bajada de Palo Oeste wells are our holdout set here. So our target, so what the model attempts to predict, is a 24-point vector of cumulative production. So rather than targeting a single production variable like 365-day cumes or an EUR, we're targeting a production curve. We also derive SHAP values or Shapley values, which we will use towards the end of the presentation to explain the predictions that the model is coming up with, to add that extra level of explainability and insight for why the model is making its predictions, which is, of course, crucial whenever you are in a process, but also for in the block evaluation phase. You definitely want to make sure that you're understanding how the model is coming up with its predictions. So moving on to the results, the first thing that we will look at today is the model accuracy, and this is for the entirety of the test set. This is 62 wells. Here we see that we're looking, the main metric that we prefer to use for evaluating error is median absolute percent error, or MAPE. And the formula for that is just the median of the absolute value of the predicted minus the actual for that well over the actual for that well. So you have a distribution of absolute percent errors, and then we take the median of that. And we can plot that error as a time series through the IPE days, going from day 30 out to day 720 at the end of our forecasts. And you see the early time error is extremely high. That's very common. You have differences in flowback. You have lots of noise going on. That's common no matter what basin you're in. But then that kind of stabilizes by the time you make it out to around IP 180, where it's in kind of the high teens. You have a little bit of error out there at the later days where you don't really have that many wells that are that old in the basin with modern completions. And you see on the right, that's what the kind of residuals cross plot looks like on a time basis. So you have predicted versus actual there. And for context, we've built models in just about every major shale basin, and this is pretty good for a public data model. It's about the same thing to what we would get in the Bakken play in North Dakota, which has a similar publicly available data set. So that was the entire test set. Now we are going to look at just the results for the Bajada de Palo Oeste. And this study, we did all the study in March, so this is looking at the Pad 1 and the Pad 2 wells. Of course, they brought on those record breakers after the shut-ins, and I'll have a little bit of that in the conclusions. But this portion of the talk and the work is focused on the first two pads. What we have here is I'm going to walk through a series of cumulative error plots where we have oil on the y-axis, and it's in meters cubed, which is in the units that are provided by the Secretaría. And then on the x-axis, we have IP day. So we're going out to 720. Each of these different panels is a well. So I have the sigla there for labeling the well keys. And then I have it labeled whether it's from the first pad or the second pad. You can also see just by the length of the production data, whether it was the first one or the second one. In the light green, we have the model oil forecast, and in the dark green, we have the actual oil that these have produced. So what you can see is that the accuracy is pretty strong for these wells, especially in the early times. The Pad 2 wells are more accurate on the whole than the Pad 1. The way that these metric scores end up overall, percent error, it's 28% over prediction for the first pad at the cutoff date, and 3% over prediction for the second pad, and then and that's kind of on the aggregate. The median absolute percent error, we get to 28% and 10%. One thing that you can see here in the production curves is at about IP 210, the Pad 1 wells are showing a kind of a divergence away from the curve, where you see that they're tracking the curve a little more closely there in the early time, and then the production curves off to the side. And that's about when Pad 2 was brought online. So it may be possible that there is production sharing or some other factor which was leading to this. We don't, because we don't know the bottom hole locations, it's hard for us to establish which wells are actually next to each other from Pad 2 and Pad 1. But just looking at these production curves, that definitely could be something which is going on. Moving on to gas, so we train a model for oil, for gas, and for water. The gas predictions and the actuals are kind of holding to a similar trend as they are for the oil. So we see that on the whole, the Pad 2 is very accurate. Pad 1 is pretty accurate in the early times, and then we see that divergence, that kind of bend in the curve away from the prediction, again, at about 210. The interesting thing here is that that's happening on all 4 wells, not just on 2 of the wells. So whether that's being felt across multiple zones or it's just some kind of an artifact, I just thought that was an interesting thing worth noting. But on the whole, these are relatively accurate gas predictions. Moving on to the water, we see that this one has much higher error than either the oil or the gas models. This is also very common for us to see higher error in the water just because by its nature it has more variability than either the oil or the gas production, at least where it's the secondary fluid. If you're in a play where water is the primary production and there's just a little bit of oil, the models are actually more accurate for the water. But here you can see that in dark blue, the actuals are the ones that are kind of all over the place. Our forecasts are relatively consistent across these wells, so who knows what's driving this. Maybe you all have some ideas about the completions or the flowback strategy or something else. Let me know if you have an idea of why there's so much variability. Maybe it's targeting, but I do think that is something that is interesting. So now I'm showing you the kind of total production values and forecasts for the oil, the gas, and the water. That's 1, 2, 3 there for both Pad 1 on top and Pad 2 on the bottom. So it's the same plots that you were just seeing, except here I've summed up all of the predictions and the actuals across each of the forecasts, or across each of the pads. So you see basically the story where you see that divergence in the oil and gas forecast, or actuals away from the forecast at about IP.
5 minutes left.
What's that?
5 minutes left.
Okay, thumbs up. And for the water, you see the error is much higher there. So next I'm going to move on to Shapley values. So these, as I mentioned at the start of the presentation, are an explainability data set that show what the impact of each of the forecasts, each of the input variables was on the forecast. And this is for the well 16211. The basic idea is adapted from game theory, and it is that the simplest prediction that you could make for a well, if you didn't know anything else and someone asked you to make a forecast for a Vaca Muerta well, you would just guess what the average production value was for the basin. Later, if you knew, okay, it's in the oil window and it used this completion design, then that extra information would allow you to move your forecast away from that average. And so the idea of the Shapley value is that the delta in the Shapley value, the Shapley value represents that delta or that force away from the model average. So the zero line here would be no impact compared to an average well. We produce a Shapley value for every variable times time point times production stream. So when we look at the average Shapley values for pad 1 and pad 2, we can ask some questions about the different completions designs or geology that was employed at these locations. So here you can see that the geologic factors and some of the spacing metrics that we calculated, those are relatively similar, but the wells in pad 1 and pad 2 did have two different designs. So Vista's kind of V1 design was on pad 1 and their V2 design was on pad 2. And you see they increased the proppant volume, increased the fluid loading, shortened the stages. And you see going from pad 1 to pad 2 that the Shapley values are showing a pretty strong impact from those decisions, that it's equal to about a 12% uplift in production compared to the average Vaca Muerta well. We can also run some counterfactuals here. So we can run hypothetical cases through this model once it's built. That's one of the nice things about having a machine learning model. So if we ran the vintage 2 designs, the V2 designs on the first pad, you see that on the right. So that's as drilled over there on the left, and with the V2 design across both pads over there on the right. And you see that the pad 1 wells that were originally kind of showing lower Shapley values for the different completion metrics, those wells have kind of moved to the right of the pad 2. So the model is basically saying that it thinks that if you had run the V2 design on pad 2, or sorry, on pad 1, that you would have seen similar or even better results than what you saw on pad 2. So that's just an example of stuff that you can do with these models in a pre-drill scenarios. You can also, or pre-lease scenarios, you can also run completions. So that's definitely an advantage of these machine learning models. We also did we ran some wells across the entire block to kind of see how the overall prospectivity would work. So I have, just a set of wells plotted for 365-day cum, and then we have a risk adjustment down there on the bottom. So our models produce uncertainty metrics. And I pay attention to the scale bar here, where we go from, and this is for 365-day cum, but we go from 10.5 meters cubed per meter to 11.6 meters cubed per meter. The model doesn't see too much of a difference across the block. But when we look at the uncertainty metrics, so we've taken that prediction and adjusted it with the P90 to P10 ratio of our model forecasts. You see that when that's done, that by far the highest risk-adjusted cum is in the southwestern corner of the basin, which is where Vista started the drilling program. The model thinks that it's possible that there's going to be nice production up there in the northeastern part of the basin, but there's a lot of uncertainty. That's just because there's not too many examples of wells that are drilled as you get that kind of shallower, lower maturity area. So in conclusion, despite the limitations of the data set, the model still performs well at predicting the performance of the Bajada, the Palo, Oeste wells. We see that both the pad 1 and 2 wells have strong accuracy, although we do see higher than forecasted decline for pad 1, which may be related to some kind of a parent-child or production sharing relationship with the second pad. Can't answer that definitively because we don't have the bottom hole locations. So we did, pad 3, you guys have probably seen the news. We wrote a whole blog post on it, but it returned from the shut-in after this paper was completed and submitted, and had the highest production that the Vaca Muerta has ever seen. Flush production probably played a role. We did run it through kind of after we had done this work. We ran it through, and we definitely did not predict that it was going to be a record setter. But that's machine learning models aren't very good at predicting the P99.9 production just to begin with. So that's not unexpected. Plus you have the issue of the flush production. So maybe we'll do some more work on that later.
Excuse me, enough presentation time. Start the question block.
Thank you.
Bueno, we thank Steve Cross for his presentation, and now we start to the questions from the public. First, from Jesus Ochoa. Are you planning on adding geology and petrophysical parameters to your models? We have seen that modeling only the engineering completions side drive to overestimated predictions.
Yeah, it's a good question. I mean, we would love to add in additional petrophysical and geological variables. Usually what we'll see when we build regional models is that the regional trends of stuff like maturity, depth, or basin facies will be responsible for a huge chunk of the variation on a regional scale. But then you can get a more accurate model by including those additional variables. So, if we can get the data set to do that type of work, we'd love to do it.
Okay. Gabriel Horowitz asked, what data from any well do you use?
What data from, what was that?
What data from any well you use for the model, I suppose.
Sure. So we use the production data, that's oil, gas, and water production. Completions, we have stage length, proppant volume, fluid volume. We normalize everything on a lateral length basis, so that's how we use the lateral length. And then we had 2 regional geologic grids. We had depth, we had seismic 2A travel time and depth. So those were joined at the well location and used as predictive features. We also calculated some very rough spacing metrics, like how many wells are on a pad, but that's highly uncertain given the not knowing where the bottom holes are.
Okay. Eduardo Barreiro asked, how many oil wells have pad 1 and pad 2, especially for water production?
Yeah, yeah, good question. We have water production for all, so there's 4 wells on each pad, and we have water production data for each of those in the database. So you can see in the dark blue here are the production values for each of those wells.
Okay. Sebastián Portela asked, from what non-public information do you think could improve the model?
Yeah, it's a great question. The first one that I think would be a big one is bottom hole locations or directional surveys. We also don't know the landing zones of these wells, so of course Cocino or Organico, we know that makes a pretty big difference in forecast. And right now the model doesn't know exactly where within the Vaca Muerta it's landed. So it's guessing basically something average or in between what the production would be for those different landing zones. So that's the source of the error. So bottom holes, landing zones, those would be the ones that I would start with for sure.
Okay. Bautista Belletiers asked for, do you try implementing a deep learning model? It could improve the performance of the study.
Yeah.
This is the last question.
Okay, yeah. We've done a lot of research with using deep learning or other neural net-based models. Generally, we find the performance is analogous to what we see with the tree-based methods. The disadvantage is that they're less interpretable. And also for a data set of only 300 to 700 wells, it may not be enough to run a deep learning model. So we're happy with how these have progressed. We haven't run one in the Vaca Muerta, but we've done plenty of R&D on those methods in North American basins. So thank you for the question, and thanks to the organizers and the moderators for the panel for doing such a good job today.